Welcome back to the channel. Today I thought we would take a look at a fun derivative, and so here it is. All right, so there's a couple of ways to do this. Since that's a power, you've got a base and an exponent, it should motivate this idea of exponential or logarithmic. So one way to do it would be to first let's identify it as a function x to the x, y is equal to x to the x. And then what I could do is I could choose to deal with this exponent x through a log rule. So if I was to ln both sides, or I'm taking the log of both sides, base e, it doesn't really matter, you can use any base you want. Take the x down, ln x. Do you see? If I take the ln of x to the x, then I can use the power rule. The x comes down as a coefficient. Okay, now I have to deal with implicit differentiation. So I'm going to differentiate through. So the derivative of ln y is going to be, well, 1 over y multiplied by the derivative of y, which is y prime. Okay, so I'm using implicit differentiation. On the right-hand side, I've got x as my independent variable, so x times the derivative of ln x, so x times 1 over x plus ln x times the derivative of x. So ln x times the derivative of x, since x is the independent variable, it's just going to be 1. All right, well, this looks pretty good because now y prime, I could just multiply through by y. So that's going to give me y prime is equal to, well, y times, well, x times 1 over x is 1, plus the ln of x. And then what I could do is replace the y, which is x to the x. So the derivative y prime is going to be x to the x all multiplied by 1 plus ln x. And that's a really common way to do it, is to basically take the log of both sides and then take the derivative using implicit differentiation. Okay, so if you're using logarithms and the laws of logs, remember you can also use exponents. So there's no reason why I can't take the number x to the x and write it as a power, okay? So e to the what would equal x to the x? Well, what I do know is that I can take any number and I can write it as e to the ln of that number, okay? And they're going to be equivalent. But you sort of think of the e and the ln as cancellation, bringing the n down into the down on the ground. So that means that x to the x can be written as e to the ln of x to the x. And this x can now be brought down as a coefficient. So that's equivalent to e to the x times the ln of x. And what I could do now is, if I want the derivative of this, and they're equivalent, I could take the derivative of that. So now I'm going to take the derivative, d by dx, of e to the x ln x. And this is all in terms of x now. Do you see? There's no y, so there's no need to be implicit. So we're just explicitly differentiating. So this is going to be equal to, well, the derivative of e to anything is e to that something. E to that something, x to the ln x. And since we have an inside function, we have to take the derivative of it. The inside function is found in the exponent. So I'm going to take the derivative of the exponent, multiply by that. So it's x times the ln of x, which is 1 over x, plus ln of x times the derivative of x, which is just 1. So ln x, close bracket. And then I could take this and just return it back to its original form. Do you see? I could bring that x back up equals e to the ln of x to the x multiplied by 1 plus ln x. And then, well, I could just take that back to its original form, x to the x, which is equal to x to the x times 1 plus ln x. And you see you get the same answer when you use logarithmic differentiation. Both methods will give you the same answer. All right, if you liked the video today, slap a like on it. Don't forget to subscribe, and I'll see you right back here in the next video.